Hiya 13. Today I'm going to talk about the final part of the proof chapter, and that's going to be the negation of a statement. So a question might ask you to provide this. So I've started off with a definition. And so the negation of a statement is the logical opposite of a truth statement. And by opposite, I don't tend to mean the extreme opposite. I mean what you'd write down if the statement was directly false. And we'll kind of go through exactly what I mean by that as we go through the video. So normally you got to find the negation of a statement by putting the word not in the sentence in the correct place. And it is important that it goes in the correct place because otherwise you might think you've got the negation when actually you don't. So as a very quick example, if you've got the statement, this suit is black, then the negation of that statement is, of course, this suit is not black. And you maybe recognize that from the scene from Borat. Right, that's quite an easy example though, and as statements get more complicated, it becomes more difficult to figure out how to work out the negation. So I have to introduce this idea of what we call quantifiers, and they appear quite often in mathematical statements that can be proved. So I'm thinking of phrases such as for all and at least one, or none, or sometimes some, and phrases like that, okay? Phrases that describe how often a certain property holds or is true. So my main advice for this video here is going to be, if you've got a statement with a quantifier in it, the place where the not is going to go to get the negation typically will go before the quantifier and not the property that's being described. So as a couple of examples, kind of in general, if you've got a statement that has this first form, that's all x have property y, then rather than saying all x have property not y, that's the incorrect place for the not to go. Instead, to negate, you're going to put the not in front of all, that's the quantifier. So the negation becomes not all x have property y. Okay, and then by kind of rearranging that and writing it in an equivalent way, it's probably better to say at least one x has property not y. Okay, that statement in red is the same as the one above. And it's probably easier to find a counterexample using that way of writing it rather than the one above. Okay, and then similarly, if we change our all statement into a kind of none statement, if you've got no x's has property y, then again, we negate the kind of none aspect of the sentence, and that would become a sum, which is the same as at least one. So the negation becomes some x's have property y, and we'd probably prefer to write at least one, by which I mean not necessarily all, but obviously at least one. Okay, so hopefully that's clear. If we see some examples, hopefully that will become much clearer as well. And again, any questions you can let me know. All right, so examples then. If I were to have the statement, all swans are white, then that follows our kind of all structure from the previous slide, and all x's are y's statement. So the negation of that is going to be what you get when you put not with the quantifier all. So that means not all swans are white will be the negation. Okay. The incorrect answer to that will be all swans are not white, which is not the negation. Okay. To show that, if we want to disprove the statement using the negation, you could easily turn that into at least one swan is not white. Okay, that's the same. So all you've got to do is find a black swan, and you've disproved all swans are white. Great. Okay, question 2. Let's do a couple of mathematical ones. None of the prime numbers is even. So using none as our quantifier here, if I negate that, I'm going to get at least 1. So none of the prime numbers is even negates to at least one prime number is even. And of course, that's going to be true, isn't it? Because we've got the prime number 2. Okay, thirdly, we've got all of the numbers between 0 and 20 have either 1 or 2 syllables. So this is another all statement, which negates to at least 1 does not have this property. Okay, all becomes not all, which is of course the same as at least 1 not being this. So our negation is at least one number between 0 and 20 has neither 1 nor 2 syllables. Okay, I've included one that has an either or in, because if I take not this property, that becomes neither nor, which of course in the context of this would be the same as saying more than 2 syllables. So hopefully you agree with that as well. If you look through the numbers between 0 and 20, you can find 17, which is the one that's got 3 syllables. Okay, great. Hopefully those examples made sense. So finally, before we finish, I want to show you examples of what to do if you've got a conditional statement as well. So we've looked at these in our previous proof lessons. If you've got a statement that has this form, which is if P then Q, which is a kind of implication statement that we've looked at, which kind of with symbolic language looks like this. So to negate a statement like this, the way it works is to say that there exists at least one P for which we have not Q. Okay, so the way to understand this, another way of thinking about this sentence is to say all P are Q, or I guess all P's are Q's, kind of might fit a bit better. So the negation is not all P's are Q's, which is the same as saying at least one P is not Q. Cool. Okay, a couple of examples before we finish off then. So if f of x is continuous at a point, then f of x is differentiable at that point. That's actually not true, and we need to negate it in order to disprove that. So the negation becomes there exists a function f of x which is continuous at a point, but it's not differentiable at that point. Okay, then check the structure of the sentence to get that correct negation. To show that's true, that negation, we can think of the function mod of x, if you like. That's probably the most easy example to think of. So mod of x, or absolute value of x, looks like this, remember? And specifically when x is 0, then at that particular point it's continuous. But you can show using the limit that it's not differentiable. Okay, great. Okay, finally then, a famous theorem I've used here that you might recognize as Fermat's last theorem. So if n is greater than or equal to 3, then x to the n plus y to the n equals z to the n has no positive integer solutions. Okay, that's in fact true, and we've known it since the 90s. Its negation, however, would be this. So there exists an n greater than or equal to 3 such that x to the n plus y to the n equals z to the n does have a positive integer solution. Okay, and bear in mind that no solutions has negated to at least one solution. Okay, excellent. Hopefully those examples made sense, and you can always contact me if you need some more advice on this. For today's lesson, please, can we go through exercise 1A from the textbook, which has plenty of practice on this. To start with, it has you negating statements, and then after that, it's got using that in order to set up and prove a proof by contradiction. Okay, because proofs by contradiction rely heavily on you being able to find a negation first of all. All right, so these questions, please, and then I'm going to set the assignment for this week due in next week. Right, fab. I'm going to leave it there. Thanks for your 13, and I'll see you soon.